My name is Alexandria Johnson. I'm a professor of practice in the Department of Earth, Atmospheric, and Planetary Sciences at Purdue University. So clouds are actually a ubiquitous feature of planetary atmospheres, and we see that from our own solar system. And so as we've gone out to look at exoplanets, it's no surprise that we've found clouds there as well. And these clouds tend to block our view of the atmosphere and the surface below, particularly when we're thinking about potentially rocky exoplanets, where we might want to look for biosignatures in life. If we learn about the clouds, we can then learn about the atmosphere below. We can think about the atmospheric chemistry at work, the climate, the way the atmosphere moves, which is the dynamics, electrification. There's all sorts of things that clouds can help us learn, even if we can't directly see that atmosphere. There are a bunch of different ways that lab work can help inform astronomy. So what we do is we collect essentially the ground truth for all of these observations, because if we can't see the atmosphere below and we can't send a probe there to get actual in-atmospheric measurements, we need to do things in the lab. And so we collect data, and this data then goes to the astronomers, and they can look for these signatures when they're observing exoplanets, or they can use it when they're modeling these exoplanets to learn more about the atmospheres. We grow clouds in the lab by trapping single particles. And so when we have these single particles around, we can pump in different gases. We change the temperature and pressure that those gases and that particle are exposed to, and we can watch the particle grow or shrink over time. And this is a process we see happen in clouds everywhere. Yes, we're not thinking about a cloud that's miles wide by miles deep, but this single particle can represent everything that can happen in a cloud.